Welcome back to AI Paper Podcasts. Today we're diving into something really fundamental for AI, especially the kind that interacts with the physical world. Robots, embodied agents.
Exactly. We're talking about understanding physical tools. Seems simple, right? But for today's big multimodal large language models, the MLLMs, it's proving to be a huge challenge.
Right, these models are often seen as the brains for future robots, but do they actually get how a tool works, or are they just pattern matching text and images?
That's the core question. And this new paper introduces something called PhysToolBench. It's actually the first benchmark designed specifically to test MLLMs on using, understanding, and even creating physical tools.
Okay, PhysToolBench. Over 1,000 image-text pairs covering daily life, industrial stuff, and it tests them on 3 levels: recognition, understanding, and creation.
And the headline finding. It's a bit of a reality check. Even the absolute best models, the big proprietary ones, they max out at around 63% accuracy.
63% compared to humans who are.
Humans are consistently above 87%, sometimes hitting over 93%. So a massive gap.
And the worst part, the biggest failure point they found wasn't even the hardest creation task. It was this middle tier thing, availability understanding.
Yes. The M3 tier. This is what they call the physical tool trap. Models just hallucinate. They see a picture of a broken tool, say a cracked plunger, and they'll still recommend using it.
So they don't visually verify if it's actually functional.
Precisely. It shows this deep lack of real visual and functional reasoning, which really makes you question how ready these MLLMs are to be reliable planners for robots doing real things in the world.
Okay, that's the crucial takeaway up front. Let's dig into how PhysToolBench actually works, because the setup sounds quite clever.
Yeah, the methodology is key. It goes back to that old Thomas Carlyle quote, right? Man is a tool-using animal. For any agent to be effective, tool use is fundamental.
It's non-negotiable, basically.
Pretty much. So the benchmark uses a visual question answering format. The model gets a task like cut the vegetable, and it sees an image with a few objects, each with a number label. And here's the crucial bit. The only things it can use are those numbered objects. Nothing else exists.
So it's constrained, and the model has to output
the number of the right tool, or maybe numbers if it needs to combine things, or, and this is important, it might have to say none if nothing suitable is available or functional.
Got it. And those 3 difficulty levels you mentioned, easy, medium, hard, let's break them down. Easy is just tool recognition.
Yeah, that's the baseline. Can it see the task, cut vegetables, and pick the picture of the knife? Basic association. Does it know what a knife is for?
Simple enough. Then medium gets trickier. Tool understanding.
Right, and this one has 3 subparts, which really probe deeper.
M1 is attribute understanding.
Exactly. This isn't just function, it's about properties. Like you need to sear a steak at 300 degrees Celsius. You've got a Teflon pan and a cast iron skillet.
Okay.
The model has to pick the cast iron because it understands high heat tolerance, the material science aspect, not just pan cooks food.
Right, understanding why it's suitable. What's M2?
M2 is tool combination. Does it get that some things need assembling, like putting batteries in a remote, or figuring out a chain of adapters and cables to connect, say, a monitor to a laptop? Multi-step stuff.
Okay, makes sense. And then M.3, the one you highlighted earlier, availability, understanding, the trap.
This is the big one. It tests if the model is actually looking carefully. The image might show the conceptually correct tool, like a plunger for a blocked drain task, but the plunger itself is visibly cracked or damaged.
So the right answer is none, because that specific tool won't work.
Precisely. It checks if the model reasons about the physical state of the object or just relies on the label plunger.
And finally, the hard level, tool creation.
Yeah, this is about ingenuity. No standard tool available. Task is tighten a flathead screw. You only have, say, a wrench and some coins.
Can it figure out a coin could work?
Exactly. Does it understand the underlying principle, like applying torque, enough to improvise? That's advanced reasoning.
Okay, that structure makes a lot of sense. It really layers the complexity. So let's talk about how the models actually did on this. The results.
Right, so they tested 32 different MLLMs, a real mix, the big names, open source models, even ones specifically fine-tuned for robotics, the VLA backbones.
And we know the human baseline is strong, 87% plus. How did the top AI models stack up? You said around 63%.
Yeah, the best proprietary ones like GPT-5 and O3 peaked around there, which is okay, but still failing over a third of the time.
That's a significant gap. Any surprises in the open source space?
Actually, yes. GLM 4.5V did notably well, hitting about 55%. better than some proprietary ones, which is interesting. Shows good training can make a difference.
But what about the models actually used in robots, the VLA backbones?
Ooh, that's where it gets stark. Models like PaLiGemma, QuinVL, they were universally below 15% overall accuracy.
15%, that's barely above guessing on some of these.
It's really low. It suggests the models often underpinning current robotics work just don't have this fundamental tool understanding.
Wow, okay. So that leads into one of the paper's main findings, right? About model size.
Finding 1, scale matters. Definitely. They found a pretty clear link, especially for open source models. You really only start seeing basic competence, like 60–70% on the easy tasks.
Just the recognition part.
Yeah, just recognizing common tools. That ability seems to emerge consistently only when models get to around 10 billion parameters or more.
So practical takeaway. For serious robotics or embodied AI, you probably need models bigger than 10 billion parameters, just as a starting point for tool sense.
That seems to be the message, yeah. You need that scale for the basics to even kick in reliably.
But size isn't everything, right? There were specific ways even the big models failed. Finding 2.
Right, the long tail problem. They're okay with hammers and knives, the common stuff. But performance drops way off for less common or more specialized tools.
And they specifically mentioned digital products, which seems super relevant today.
Hugely relevant. They struggle with subtle visual differences. Is that an HDMI or a DisplayPort cable? Is this USB-C or Lightning? They often just see cable or port.
Which means they can't plan tasks involving them correctly.
Exactly. The paper gives an example. Connect a monitor to a laptop that only has Type-C ports, using a Type-C to HDMI adapter and an HDMI cable. If the model can't visually distinguish those parts, the plan falls apart.
Okay, that makes sense. And then finding 3 was kind of surprising. The model specifically trained for robotics didn't do much better.
Yeah, that was a big one. Models like RoboBrain 2, fine-tuned on lots of robotics data, showed basically no significant improvement over their base MLLM on this benchmark.
Wait, really? So all that extra robotics training didn't help them understand tools better?
Apparently not for this kind of deep functional visual understanding. The hypothesis is maybe current robotics data sets are good at teaching actions, grasp this, move here, but they lack rich data on tool properties, tool states, damage detection, that kind of thing.
So we're teaching them how to move, but not how to properly assess their equipment first.
Sort of, yeah. Which brings us back to the absolute biggest issue they flagged finding 4. That failure in availability understanding, the M3 tier.
Right, the fact that recognizing a broken tool, M3, was harder for models than inventing a new tool, hard tier. That still feels backwards.
It totally is counterintuitive. But the reason seems to be that MLLMs are heavily biased towards their language training. They see syringe, and the strongest association is draws blood.
The textual concept overrides the visual evidence.
That's the idea. Verifying the physical integrity is the needle bent, is the barrel cracked. It's a harder, more visual reasoning task. So they default to the text association and essentially hallucinate that the tool is fine.
And the real-world danger there is huge, using a faulty medical instrument.
Exactly. It's not just about the task failing, it's about safety. Trying to use a broken tool could be actively harmful. That failure mode is way more dangerous than just not being able to figure out how to improvise.
Okay, so the problem is clear, the stakes are high. What about solutions? Did the paper explore ways to improve this? Reasoning, maybe?
Yeah, they looked at reasoning. Finding 5 is basically reasoning helps, but current methods aren't enough on their own.
How'd they test that?
Using chain of thought prompting, COT, giving the model space to think step by step did lead to better scores, like Quen 2.5 VL72B improved by almost 3% overall with COT.
Okay, so prompting helps. And models built for reasoning.
They tend to do better baseline, yeah. GLM 4.5V, which did well overall, is known for stronger reasoning capabilities. But even then, the reasoning can be brittle.
Brittle how?
Like poor spatial or physical intuition. The paper mentions models failing to realize a correctly sized flathead screwdriver can often work on a Phillips screw. They're stuck on the canonical definition, not the geometric reality.
Yeah, too literal, not enough physics sense. So COT helps a bit, but isn't the whole answer? Did they propose anything else?
Yes, and this seems really important. They propose a framework called Vision-Centric Reasoning, or VCR.
Vision-centric, so forcing more focus on the image.
Exactly. They argue MLLMs suffer from modality bias. They lean too heavily on text, ignoring crucial visual details, especially subtle things like damage or how things fit together.
So how does VCR work?
It breaks the process down. First, a quick global analysis of the whole scene. Then, crucially, in-depth analysis. It uses an object detector, like DinerX, to draw bounding boxes around the specific tools.
Okay, isolating them.
Right. And then it forces the MLLM to analyze the cropped images from those boxes in detail. Really zoom in and look.
And the third step.
Multi-level evidence integration. It combines the understanding from the overall scene with the detailed insights from the cropped tool images to make the final decision. It's about making sure the visual check happens and influences the reasoning.
Does it work?
Apparently, yes, especially on the really tough part, that M3 availability tier. Applying VCR gave GPT-5 an 18% performance boost just on recognizing unusable tools.
18%, that's huge, just by forcing it to look closer.
It strongly suggests that visually grounding the reasoning is absolutely key to overcoming that physical tool trap, that hallucination problem.
Okay, so wrapping this up, PhysToolBench really shines a light on a major gap between current MLLM abilities and what's needed for reliable physical interaction.
Definitely. It quantifies the limitations and pinpoints that critical failure, not being able to visually confirm if a tool is actually usable. The difference between human intuition and AI performance here is still vast.
And the path forward seems twofold. We need bigger, generally more capable models as a foundation.
Right, likely over that 10 billion parameter mark for starters.
And we need much better training data, specifically data that focuses on tool functionality, damage, material properties, the stuff current robotics data sets seem to be missing.
Exactly. Better backbones and better, more visually focused training data.
Which leaves us with a pretty critical thought for anyone working in this space.
I think so. If your AI agent can brilliantly plan a complex task, map out all the steps using various tools, but it can't tell if the one crucial tool it needs is broken right in front of it.
Yeah.
What does that really mean for the reliability and safety of that agent, especially if you deploy it in manufacturing or medicine or anywhere things can actually go wrong?
A lot to think about there. Definitely highlights the work still needed before these models are truly ready for complex, real-world physical tasks. Okay, that's our look at FistalBench. Thanks for joining us on AI Paper Podcasts.